In a recent study, the real colors of the planets Uranus and Neptune are attempted to be better predicted by comparing the reprocessed versions of single-filter images with the images published shortly after the close encounters Voyager 2/Uranus and Voyager 2/Neptune made in 1986 and 1989, respectively. The images of Neptune have appeared to have a deep blue tone for decades, while Uranus seemed more greenish. However, according to a study published in the monthly notices of the Royal Astronomical Society, the true colors of these two ice giants in our solar system might be a pale greenish-blue. Images and reality. NASA's Voyager 2 mission is the only spacecraft that has passed close to both ice giants, providing the first detailed images of these distant planets. In 1986, Voyager 2 passed by Uranus, revealing images that depicted a faint bluish or blue-green planet. In 1989, the spacecraft passed by Neptune, capturing images of a deep blue planet. However, astronomers had long realized that the most modern images of both planets did not reflect their true colors accurately. Voyager 2 captured images of both planets in different colors, and these monochromatic images were later merged to create composites. These composite images were not always well balanced, leading to the misconception that Neptune appeared much bluer than it actually was. The contrast of the first images sent by Voyager of Neptune was enhanced to better highlight the clouds and winds on the planet. Patrick Irwin, an astronomer at the University of Oxford and co-author of the article, states in a statement, while Voyager 2's familiar images of Uranus were published in a form close to the true color, those of Neptune were actually stretched and enhanced to look artificially very blue. He continues, this artificially saturated color was known to planetary scientists at the time, and the images were published with explanatory text, but this nuance has since been lost over time. In the new study, the research team applied data obtained from the Hubble Space Telescope's Imaging Spectrograph, STEES, and the Multi-Unit Spectroscopic Explorer, MUSE, located at the European Southern Observatory's Very Large Telescope. STEES and MUSE provide data where each pixel carries continuous color spectrum information. Therefore, by processing observations more precisely, the colors of the planets can be more accurately determined compared to the colors seen through filters. Using this data, the research team rebalanced the composite color images recorded by Voyager 2's internal camera and the Hubble Space Telescope's Wide Field Camera 3. As a result of this reprocessing, both Uranus and Neptune were revealed to have similar colors, displaying pale greenish-blue tones. While Neptune includes a slightly bluer tone, the model showed that this color is likely due to a thin layer of haze on the planet. The study also provides a possible explanation for why Uranus undergoes a slight color change during its 84-year orbit around the Sun. The research team initially compared Uranus images with brightness measurements of the planet taken in blue and green wavelengths from 1950 to 2016 at Lowell Observatory in Arizona. These measurements showed that Uranus appeared slightly greener during the summer and winter solstices when its poles were facing the Sun. However, during equinoxes, when the Sun is over the planet's equator, it appeared more bluish. One of the known reasons for this change is Uranus' highly unusual rotation, as the planet almost rolls on its side while orbiting. During the solstices, the north and south poles almost directly face the Sun and Earth. Changes in reflectivity in Uranus poles, according to the authors of the article, significantly impact the planet's overall brightness when observed from Earth. Astronomers were not entirely sure how and why this reflectivity was different. The research team developed a model to compare the color bands in the polar regions of Uranus with equatorial regions. As a result, they discovered that the polar regions were more reflective in the green and red wavelengths compared to the blue wavelengths. Uranus is partially more reflective in these wavelengths because methane gas absorbs red light, and the amount of methane in Uranus' equatorial region is about twice that near the poles. However, these factors were not enough to entirely explain the color change. Therefore, the research team added a new variable to the model, representing a cap of progressively thickening icy haze observed when Uranus transitions from equinox to summer solstice. This haze is believed to be made up of methane ice particles. Simulating this pole change in the model, the icy particles increased the reflectivity of Uranus in the green and red wavelengths. The model explained that Uranus appeared greener during the solstices due to the decrease in methane and the thickening of methane ice particles near the poles. Heidi Hamel, a researcher at the University of Leicester, says in a statement, "In addition to the misconception of Neptune's color, Uranus's unusual color changes have been bothering us for decades." She continues, "This comprehensive study finally resolves both issues." Hamel is not among the authors of the new study. Closing the gap between the public perception of Neptune and its true appearance illustrates how data can be manipulated to showcase or enhance certain features of a planet for aesthetic purposes. Lee Fletcher, a co-author of the article and a researcher at the University of Leicester, says to the New York Times, "There has never been an attempt to deceive." He continues, "But there was an attempt to take these data and perhaps make these beautiful scenes more meaningful than just a blurry, gray, indistinct smudge in the distance." Don't forget to follow for more information.